Hi, my name is Deborah Kitzler, and this is my lab report for the third lab in Physics 2211. In this lab, we examine Newton's second law once again. Newton's second law states that the acceleration of an object is directly related to the net force and inversely related to its mass. In this lab, we specifically examined the net force of one object acting upon another, with the net force between them being the gravitational force, which we will examine later. In this lab, we created a randomly generated model of a star orbiting a black hole using our Georgia Tech email, which you can see mine below. We then utilized the position data which GlowScript gave us to obtain the path of this object and then compute the mass of the black hole which this star was orbiting. In order to do this, we utilized the position to determine our velocity, the velocity times the mass of the star to determine the star's momentum, and then we set the net force equal to the change in momentum over change in time, and the change in time was given, which was 1 day, which was 86,400 seconds. The mass of the star was also given to us, and it is 2.0 times 10 to the 30th kilograms. Once we computed the net force, we set this net force equal to the gravitational constant times the mass of the star times the unknown mass of the black hole, all over the distance between the black hole and the star squared. As you can see, the three arrows pointing towards the black hole are indicating of the change in momentum in the perpendicular and the parallel directions, and the orange arrow shows the net force. Now, if we look more closely at our GlowScript code, we can see exactly how we calculated the mass of the black hole. We first calculated the initial and final velocity of our star using its position. Then we use the change in velocity, or the velocity times the mass of the star, to calculate the momentum. Then we use this change in velocity times the mass of the star to determine the change in momentum, which is also equal to the net force. We then determine the mass of the black hole by multiplying the magnitude of the net force times the magnitude of the distance between the black hole and the star squared over the gravitational constant times the mass of the star. We then calculated the components of the force acting upon the star in the parallel and perpendicular directions, which are the two arrows you can see in the bottom right, indicated in blue and pink. The parallel component is equal to the magnitude of the change in momentum over the change in time in the direction of the tangential velocity of the star, which is p hat. The perpendicular component is equal to the net force minus the parallel component, because we know that the net force is equal to the perpendicular component of the change in momentum plus the parallel component of the change in momentum. The result given to us was the mass of the black hole is equal to 1.24 times 10 to the 34th kilograms. And as you can see below, this is one example of the calculation that GlowScript would have done. At the given position of 4.17 times 10 to the 12th in the x direction and 1.27 times 10 to the 12th in the y direction, and this is the position of the star, and the black hole is at the origin, which is the 0 vector, the magnitude of this distance between the two objects would be equal to 4.36 times 10 to the 12 meters. Now, if we plug this into our formula using the net force given, which is 8.7 times 10 to the 28th, this distance over the gravitational constant, which is 6.7 times 10 to the negative 11, times the mass of the star, which we were also given, we will result in a mass of the black hole being equal to 1.24 times 10 to the 34 kilograms. Now, what does this mean? How does the net force and its components differ from the change in momentum and its components? Although we know that the change in momentum over time and the net force have the same numerical value, the change in momentum over change in time is a result of analyzing the motion of our star, or the motion of our object, and the change in velocity of this object. Net force in this case was found by analyzing the gravitational force acting upon the star. And the net force will always point towards the center of the black hole, or towards the black hole, the center of the circle of rotation. We can also ask ourselves the question, what if the black hole had been exchanged with a different black hole? Well, because our formula did not utilize the mass of the black hole, it only utilized the position of the star, if this new black hole did not alter the path of our star, then our calculations would result in a black hole of the same mass. Therefore, there would have been no change. Thank you.